Hi there, welcome back to the formulaic approach. Now in this video we are going to be talking about organic chemistry, primarily 30 things that you must know in organic chemistry. Now the initial purpose of this video was to help students who are just starting out in organic chemistry and so maybe are grappling with some things. But now that I think about it, it's also useful for students that have done organic chemistry in the past but cannot recollect some things. So one of the things this video will help you to do is to be able to rebuild your information, your knowledge of organic chemistry, and make some of these things stay with you. Do you understand? So, but of course, if you are just starting out, so this video is going to help you. And of course, in order not to defeat the initial purpose, I'm going to start from the scratch. Okay? So, 30 things you must know. So let us get to it. If you are doing O level or A level, this video is really going to help you build a solid foundation in organic chemistry. So let us go. And in the meantime, do want to subscribe to the channel. The first thing we want to talk about, of course, is number one, organic chemistry itself. Okay, so what is organic chemistry? So primarily we are looking at the history, okay? The history, okay? Historical development of things, all right? So let's look at the historical development of things first. So first we must know what organic chemistry is. Now organic chemistry is basically the branch of chemistry that studies the compounds of carbon apart from the carbonates, bicarbonates. I'm going to write that on the board, but I first want to show you something. That the word organic actually refers to life, okay? So historically speaking, organic chemistry was studied as the chemistry of life. Was studied as what? The chemistry of life. So that's why it's given the name organic chemistry. Now, of course, we know that it expands beyond that a lot. So, but why did they retain that name? Now, I'm also going to be spelling out some whys in this video so that you remember some things for those that have studied organic chemistry before, and those that haven't, you understand why you are doing the things you're doing in your class. All right, so now why did the name organic chemistry stick till date or remain till date? Now, the reason is because this organic chemistry is a branch that also helped us to be able to decipher the fundamental basis of life in the molecular level, at the molecular level. Do you understand? So we were able to understand life at the molecular level, the molecules that we are made up of, the molecules that plants are made up of. Earlier in those days, it was just plants and animals that they knew as far back as the 18th century. So in those days, because it was only associated with substances that were extracted or found in plants and animals, so they called it organic chemistry. And of course, it's stuck till date because, or it remained that way till date because now we are able to study advanced stuffs as related to life still. Do you understand? So that's why it's still called organic chemistry. So I said it is the aspect that studies the compounds of carbon, excluding the following. Excluding one, the carbonates of carbon. It doesn't include the carbonates of carbon. So all other compounds excluding the carbonates of carbon. Okay. Of course, bicarbonates as well. It doesn't include them. Bicarbonates. Okay. Carbides too. Carbides are not included in organic compounds, okay, in organic chemistry, the carbides, okay. Also, what else? Carbonates, bicarbonates, and carbides. So those guys are not under organic compounds. They are under inorganic compounds. The oxides of carbon as well. The oxides of carbon, they are also what? They are also not included in organic compounds. All these guys are inorganic compounds. They are inorganic, so they are under inorganic chemistry. They are studied under inorganic chemistry. Okay, so that's what organic chemistry is. So, but historically, like I said, since it was basically plant and animal origins that we found organic compounds from. Organic compounds were first derived from plant and animal origins in those days, in the 18th century. So by the 19th century, actually, a certain man now proposed the theory of vital force, okay? We call it the vitalism theory, okay? Vitalism theory. So, and it was propounded by a certain J.J. Berzelius. J.J. Berzelius. Now, J.J. stands for Joseph Jones Berzelius. Joseph Jones Berzelius. Jacob, rather, not Joseph. Jacob. Jacob Jones Berzelius. Now, in certain texts, you see that he propounded this law in 1828. Now, actually, it is usually confused because I think I've also read a text before where I also taught my students that it was propounded in 1828, but actually, no. It wasn't propounded in this year, it was actually propounded in 1807. So some texts also say 1809, okay, because it wasn't really, I don't know, some texts just get it differently, okay, but it's actually 1807 from the research I later made, okay, because one of my students said he read it somewhere, and so I needed to make the research, okay, so it's actually 1808. I think I've taught it to be 1828 before. So Joseph Jones Jacob Jones Berzelius propounded the theory of vitalism in 1808, and what he said was that organic compounds could only be synthesized from plant and animal origin. Plant and animal origin. Okay? Only. And that in order to synthesize organic compounds, there is need for a vital force. Okay? So the synthesis of organic compound required what? A vital force, what he called a vital force. And this vital force was only available, the vital force is only available in plants and animals. Only available in what? Plants and animals. So only these plants and animals have this vital force, which was necessary for the synthesis of organic compounds. Okay, and of course, it wasn't really in the wrong then, because in those days, all organic compounds that they had found out in those days were plant extract or animal extracts. So the origin was primarily plants and animals. So you will not criticize him to have propounded such a theory. But of course, the theory was shattered by a certain. He was a Swedish scientist, a Swedish chemist. Okay, was a Swedish chemist. But another scientist, a German chemist named Friedrich Wöhler, okay, Friedrich Wöhler. Now, in 1845, was the one that first shattered the 1828. I'm sorry, 1828. 1828. So sometimes you might get the years confusing, okay? The years are not so compulsory, it's just for some of you that are taking chemistry courses, they might ask you these years, okay? So the theory was propounded in 1807, but the theory was disproved, okay? It was disproved. Disproving of vital force theory. So I call it VFT, okay? So now, Friedrich Wöhler, a German scientist, was the first to disprove that. Now, how did he disprove it? So he was able to synthesize, he synthesized for the first time, albeit by mistake, okay? It was also actually not his, it was by accident, okay? He synthesized this guy, urea. He synthesized urea from ammonium cyanide. Ammonium cyanide is an inorganic compound. It's an inorganic compound, okay? With the formula CH4CO and NH4CON. So, and he synthesized by heating, he heated this guy and he was able to produce CONH2. So this NH2, NH2, okay, yeah, that's urea. So this is the formula of urea, and this guy was able to ammonium cyanide. So this guy was Federicola was able to heat this guy. So this is heat, okay? Was able to heat this guy in the laboratory, and by accident was able to synthesize urea, okay, which was one of the products of metabolism in animals, okay. So having been able to do this, he was able to shatter this theory. Why? Because from this theory, he was able to get that it did require plant and animal origin rather, to synthesize an organic compound. This is an organic compound, okay? This is an organic compound, okay? And then one of the things that the vital force theory also propounded was that organic compounds could not be synthesized in the laboratory, cannot be synthesized in the laboratory. But he was able to do that. Okay, so that was why it was shattered. Another thing was that he also saw that the vital force there was nothing like vital force. Okay, that was what he actually disproved. He also was able to prove that there was nothing like vital force needed for the synthesis of this guy. So that's Federicola, and of course other scientists like Colby, okay, was able to synthesize acetic acid in year 1845 now. He was able to synthesize acetic acid laboratorily from the component element. This other guy too. Actually, there's another misconception. Michael Faraday actually synthesized in the year 1825, he synthesized benzene, okay? But what he did was, he didn't necessarily synthesize benzene. What he did was isolated. It was isolation of benzene. So he isolated it from what is called illuminating gas. And what do they call illuminating gas? Was coal gas, basically. Coal gas, because it's burned with luminous flame, so it was used as an illuminating gas. So he was able to isolate benzene. Okay, so some teachers might test you that was it this that was that revolutionized organic chemistry field, or the disproval by Federicola in 1828. So it was his that revolutionized organic chemistry, not Faraday's synthesis. So there are many other things, such as Auguste Kekule, who propounded the structure for benzene in 1865. Those are the other things you should know about the history of organic compound. But these are the most important ones that people commonly ask about in your exam. I mean, of course, then you should also learn structure. I'm going to deal with structure today. I'm going to deal with structure. Okay, I'm going to deal with structure. We'll still get to structure. So types of structures. So, but this one will be drawn somewhat like this. So I'm going to explain why the atoms you are seeing there, they are at angles like this. Okay, I'm going to explain why as we continue. Okay, so that is what you should know about organic chemistry. Now, the next thing we want to learn about is what are actually let's now talk about why do we study organic chemistry. Why do we study organic chemistry? So that here we'll talk about the uniqueness of carbon. So that's primarily what we want to talk about now. The next thing is the uniqueness of carbon. Number 2, why study organic chemistry? It is because of the uniqueness of carbon. Now, why is carbon unique? Now, I also talked about this in my alkane series. So make sure that I'll link a set of videos in the description. So make sure you watch those videos in the successive order that I list them. It's going to help you after you have built this foundation. So now, what is the uniqueness of carbon about? It's just about the fact that carbon has the following properties. So the first property will be that carbon is tetravalent. Okay, carbon, the tetravalency of carbon, that's what it's called, the tetravalency of carbon. I'm going to explain each one. The next one is the covalent nature of carbon. No, the next one should be the most important one, which is actually catenation, ability of carbon. In fact, this is the most important uniqueness of carbon. It's the most important, take note of that. It's the most important uniqueness of carbon because carbon is not the only guy that is tetravalent. Albeit also, carbon is not the only element that can catenate, but it is the one that forms maximum catenation, that shows maximum catenation. Are you getting it? Okay, so the next one is we know of catenation, then the covalency of carbon, or the covalency of carbon, ability of carbon to. There's also ability of carbon to form multiple bonds. Okay, multiple bonding shown, multiple bonding. Okay, and then covalency. So the way to remember is just TCMC, I don't know, MCTC. Anyways, so now let's talk about the tetravalency. Since it's like a crash course, okay? So that's why I'm jotting this way, okay? So make sure you are paying attention. So the first one is the tetravalency of carbon. Now, what is tetravalency? Tetravalency, the word tetra means four, right? So it means that carbon is able to form 4 bonds around it, okay? It's able to form 4 bonds around it. So meaning that, in a way, we are saying that the valency of carbon is what is 4. And the reason it is so is because carbon has 4 lone pairs. Do you understand? 4 lone pairs. So if there are 4 lone electrons around carbon in the outermost electron shell, it means that it can coordinate to 4 bonds, okay? Carbon is able to coordinate to 4 bonds, coordinate with 4 bonds rather. So what does that mean? It means that it needs carbon. It means that carbon needs 4 more electrons, 4 more electrons to achieve stable octet, to attain, not achieve, to attain stable octet. Alright, so using the octet rule, we know that there must be 8 electrons surrounding the atom. So if the outermost electron shell, okay. So for carbon, it has 4 electrons in its outermost electron shell, and it needs more electrons to attain stable octet. 4 more electrons, okay. So what that would look like is, if we wanted to write the octet rule electron configuration, it would be 2, 4. Okay, because carbon is number 6. Do you understand? But of course, the modern electron configuration will look something like this: 2s2, 2p, 1s2, 2s2, and 2p2. Okay, so what it does is that it does what is called hybridization. It hybridizes. I'm going to show us after. In fact, that's what we'll discuss next. Hybridization. You understand how it is, because looking at this, according to Horn's rule, Horn's rule now, I'll link that video in the description too, that says that electron entering orbital singly first. Maximum multiplicity, that is Pauli's Horn's rule of maximum multiplicity, that each shell or orbital rather, each orbital, Horn's rule of maximum multiplicity says that each orbital must have a maximum of 2 electrons. Now, and those 2 electrons must be filled singly first before pairing. So, if that's the case, then the maximum number of electrons that can enter the s orbital is 2, meaning that this guy is balanced, isn't it? Or stable. But why is it that? So, if anything, we are saying that this P, which can take 6, need 4 more, right? But actually, that's not the case. That's not the case with carbon. Okay, carbon is not the 2p orbital that takes the 4. No, I'm going to explain how that happens here using hybridization. It was a concept that was propounded by Pauling in order to explain the tetravalency of carbon. How carbon is able to coordinate with 4 bonds around itself. So what that means is that in the organic chemistry course, you are going to be seeing 1, 2, 3, 4. Is either you see this or see something like this or see something like this. Now, what this means is that each of these carbon are going to have 4 bonds around it. 1, 2, 3, 4 for this guy. These are single bonds all through. We have a name for it. Now we have 1, 2, 3, 4. This is also 4 bonds, but this one is not a double bond. Is that okay? Now look at this one. Each carbon here has 4 bonds too. 1, 1, 2, 3. That's 4. 1, 2, 3, 4. For this carbon as well, 1, 2, 3, 4. You notice that I counted the same bond for this carbon and for this carbon. Exactly. So this bond that they share is for both of them. Do you understand? It is counted for both of them. So that's tetravalency. Whichever the kind of bond it's forming, whether it's a single or multiple, you must make sure that each carbon has 4 bonds around it. 4 bonds must be around each carbon. That's the tetravalency of carbon. And then speaking of sharing that I just mentioned here, that's where we get to the covalency. The covalency of carbon. I'll talk about catenation soon. The covalency of carbon. Now, what is covalency? What does the word co mean? It means together, right? So, what does that mean? It means that carbon engages in a covalent bond. And what is associated with covalent bond? There are 2 major types of bonding. Actually, 3, but we mostly speak of 2 for most of our compounds. We talk about ionic bond and covalent bond. Ionic bond or electrovalent bond is one where electron is transferred from one atom to another. There's total transfer of electron, usually from the electropositive guy, which is a metal, and it's being given or transferred to the electronegative guy, which is usually a non-metal. But in covalent bond, there is no total transfer, but a sharing of electron. There is a sharing of electron. And what does sharing of electron mean? It means that I have some electrons, but I am not complete, so I'm not stable. The other guy too is not stable. So what we'll do is, rather than give to the other, we'll come and share our electrons together. So for example, oxygen is able to form oxygen molecule here because the first oxygen is number 8, so has 6 valent electrons. The second oxygen has 6 valent electrons. So the octet structure is going to look like this. The octet structure is going to look something like this. Let me draw it here. For this guy to look something like this, first 1, 2 electrons, the next guy 1, 2, 3, 1, 2, 3, 4, 5, 6. Now this is the way we should draw it actually. So how many electrons more does this guy need? It needs 2 more electrons. That's why you see O2 minus to show you that the oxidation number of oxygen is 2. So the second guy is exactly like this. Okay? So I'm just writing this one like this now. So what would they do? So this guy needs 2. So this guy should actually give this guy 2. Okay, if I mean, I don't know. That's if it's an electrovalent bond. But this is not electrovalent. Both of them are needers. They need electron. They're electron hungry. So that's what we'll talk about in electronegativity. So what would they do? Rather than this guy giving out the 2 electrons, they will share it. So what they will do is that eventually they will come together and then you see something like this. So let's bring these 2 electrons here. Then this one will bring its 2 electrons here. This guy too, those 2 unassociated, unpaired electrons, they will come here as well. Do you understand? So that the other guy too will look something like this. So you know that these 2 belong to this guy here, these 2 belong to this guy here. Then this guy already had 4 somewhere around here before, right? So something like this. Then the inner shell is like this. So this is the shared electron here. So this is covalent bond. So also carbon is able to form covalent bond, but with what? With itself. It shares electron with itself and with hydrogen. It shares electron with itself and hydrogen. So what you are seeing here in its tetravalency here is that a carbon atom that has, remember, it has 4 it needs 4 electrons, right? It needs 4 electrons. So what to do? Okay, this is oxygen. Oh, sorry. This is oxygen. So for carbon, what it will look like is like this. You know, carbon is 2, 4 because it's number 6. So the this structure will look like this: 1, 2, 3, 4. So what will happen is that hydrogen is number 1, so it will look something like this in the s orbital. So this hydrogen will come and attach itself here. So it will share this electron that is from carbon with it, and the carbon will share its own electron. So this hydrogen, this is carbon. Another hydrogen will come here, they will share electron, the 2 electrons. Another hydrogen will come here, they will share the 2 electrons. Another hydrogen will come here, they will share the 2 electrons. So you can already see that there are 4 hydrogens linked with this guy. So what you're seeing here, this is their structure here. Do you understand? All right. So that said, I hope we now understand what covalency is. Now, let's talk about the multiple bonding, catenation. That's very important. Let's talk about catenation now. Now, catenation is basically the ability of carbon to form long chain with itself, long, consistent, and stable chain with itself. So, now, carbon is the only substance, is the only element that can form long chain with itself. That is, it can bond with itself multiple times, repeatedly, and it's going to form a very large molecule without that is stable, that will not that is stable at room temperature. Do you understand? And that also leads us to multiple bonding. Now, multiple bonding is basically talking about the ability of carbon to form single and double and triple bonds. Okay, so we have C to C bonds. We also have C double bonds, C bonds like this. I'm drawing the skeleton. This is what we call skeleton. Okay, but this skeleton is not structural formula, because it's not a formula yet. In structural formula, I will show you skeletal structure or skeletal structural formula. This one only shows the carbon skeleton. Okay, the carbons written without the hydrogen is just carbon skeleton. So now I now said this catenation is its ability to form C to C to C to C continuous like that, and they are consistent. Then multiple bond is the ability to form single bonds, double bond, and triple bond that are stable at room temperature. Do you understand? Carbon is the only one that can do this. So this is the reason why we study, or these are the reasons why we study organic compounds, organic chemistry, because they are carbon shows the following uniqueness: tetravalency, catenation, and multiple bonding, and covalency. Now, in our set, we'll talk about hybridization next. Hybridization. So let's quickly talk about hybridization now. So now, what is hybridization? Hybridization is basically the mixing of orbitals. See, the word hybrid, you should already know what an hybrid is. You know how crossbreeding is done for animals, such that you make an hybrid, right? A hybrid, rather. So the same way, to be a hybrid, yes, not an hybrid. A hybrid. Now, in this case also, what we are doing is basically mixing orbitals, mixing electron orbitals to form a new one, known as a hybrid. Now, the new one that is formed is going to be called a hybrid. Now, why is that new one called a hybrid? Because a hybrid, in biology, there's something called heterosis or hybrid vigor. Now, heterosis is when two genes are linked, pair up. Okay, two genes from different parents, they pair up. They combine the unique properties of those two together and make a special attribute of that new thing that is formed, maybe new organism that is formed, that helps it to even survive than its parents, than the initial origins. Okay, maybe not just survive, that just give you a special attribute over its parents. Do you understand? So, for example, a daughter might be more beautiful than the father and mother. The same way here, a hybrid is also different from the parent, because the hybrid will combine the characteristics. It combines the characteristics of both orbitals. So, for example, if a s orbital and a p orbital they mix together, they will form a s They form an sp orbital. Now, in an sp orbital is different from s orbital and is different from p orbital. Of course, I am assuming that you already know what s orbital is, p orbital is. If you don't know, see my video in the description below. Now, sp orbital is a new orbital different from s and p individually. Is that okay? It combines the characteristics of both s and p orbitals. Is that okay? I'm going to teach you the types of hybridization. Now, how does hybridization occur? So, it is the way Pauline was able to explain to us the tetravalent nature of carbon, which is not born from, I said that the p orbital is able to house 6 electrons. If you remember, we have spd, s can house 2 electrons maximally, p maximum is 6, d maximum is 10, f maximum is 14. So p can house 6 electrons. So you might be forced to think that, given that this is the modern electronic configuration of carbon, that it is the 4 electrons that are lacking here that is being given to it. No. That is not the way carbon is forming covalent bond here. What happens is that when carbon reaches what is called the excited state. Now, excited state. Now you see this state here. This configuration here is called the ground state electronic configuration. In the ground state electronic configuration, GS for ground state, we have 1s2, 2s2, 2p2. So what happens is, if you want to draw the orbital structure, it's going to look something like this. 1s2 will be here, 2s2 will be above, 2p will also be above. Okay, so you know that this one is degenerate into 3 shells, right? So that's why we have into 3. Now those are 2px, 2py, and 2pz. Now this guy, you want to fill the electrons inside this guy. Following Hund's rule, singly first, of course, it's not apparent in non-degenerate orbitals, so it's very easy. We just we only follow whose rule here. We only follow Pauli's exclusion principle. That is, they must have opposite spins, right? So here we have one down like this, up and down, right? But for this degenerate orbital, it is degenerated into 3 orbitals here. So to fill, we need to fill 2. So this is where we fill up and down. Now, if you fill up and up, that is, you are against Pauli's exclusion principle. Not Pauline, no, that one is Pauli, okay? Now, the point is now this. The point I'm trying to stress is this. I'm sorry. Up and up, not up and down on this. That's what I was trying to say. You feel singly first, you'll be disobeying Hund's rule if you feel like this. If you feel it like this. 1, 2, you're wrong. You have disobeyed 2 rules here, Hund's rule and Pauli's exclusion principle. And to even do like this, you are still wrong because you have disobeyed Hund's rule. Hund's rule says that we should fill the electrons singly first. So 1, 2. Is that clear? So this is the correct ground state electron configuration and orbital structure of carbon. But how about in its excited state? How does carbon, what does carbon do in the excited state? So in the excited state, nothing happens to this guy. So I'm going to show only these guys. You see these guys, because they are at almost equal, energy levels. The energy level, in fact, the energy level is equal, it's still 2, okay? Actually, because one is in P, S is in, one is in S. One is S, the other is P. P is at a slightly higher energy than S, but we're not getting into that. So, but because the energy level is almost the same, there is something that carbon is able to do. Now, it's called promotion. Now, carbon is able to promote electrons. Now, you see that according to this 2py, 2pz. Now, according to this structure here, carbon, the electrons in carbon only stop at 2py. The 2pz is empty. So what carbon is able to do is this. It will promote an electron from this 2s to promote it to the 2pz, such that when it promotes it, what will happen is that this guy will leave here in its excited state and come here. No, let's draw it again. So it will look something like this. And notice that I have drawn them together. Yes, there's not a mistake. Now, this is 2s. Notice, so it will now have 1 electron. It has promoted 1 there, then you have 1, 1, 1 here. So we have 2px, 2py, 2pz. Now what happens is this, that carbon here has, after promoted one electron, it has amalgamated both orbitals. Amalgamated means joined both orbitals. So in this case, how many orbitals are joined together, are mixed? There are three orbitals that are mixed. There are four orbitals that are mixed. We have, and it gives rise to a type of hybridization called the sp3 hybridization. There are three types of hybridization that we'll learn here. We have the sp3, sp2, sp hybridization. sp3, sp2, and sp hybridization. Keep in mind also, however, that there are more hybridizations generally, but these are the three that are of consequence to organic compounds the most. So sp3 of hybridization is where one s character, as you can see here, mixes with 1, 2, 3, 3p characters. Is that clear? Okay, so and in percentage it will mean 25% of this, while we have 75% of p orbitals. Okay, now in sp3 hybridization we have the following characteristics. Number one, we have saturation. We have saturation, and we'll still deal with that. We'll still deal with what saturation is. Now we also have, it is common with alkanes, okay, it is found in alkane, and these ones are notable for what? Single bonds. So where there are single bonds around a carbon, that carbon is sp3 hybridized. I repeat, where there are single bonds around a carbon, that carbon is what? sp3 hybridized. Then someone will ask, Master, what about cyclo group or cyclic hydrocarbons? We'll still deal with that. For those of you that already know what cyclic hydrocarbon is, as far as single bonds, like this, for example, this is cyclopropane. Now this is sp3, sp3, sp3. Even though it has two less hydrogens than the normal aliphatic alkane, acyclic alkane, it is still sp3. All the carbons there, all the three carbons there, they are sp3 hybridized. Some people might not understand what I just drew here. Don't worry, I'll still get there. Okay, so now we have single bonds, and it forms sigma bonds. It gives rise to sigma bonds. Okay, and bond angle between all the three carbons when they form on the bond, between all the bonds, the bond angle is usually 109.5 granotes, or 109 degree 28 minutes. Approximately this, or 109 degrees 28 minutes. So that is that about hybridization for this guy, sp3 hybridization. Now, and the shape that it forms is the tetrahedral geometry. Tetrahedral geometry. Now, how about this guy, sp2 hybridized? Now, you know in sp3 we say that who and who we hybridize? This 4 orbitals we hybridize. 1, 2, 3, 4 orbitals. In this case, how many orbitals are you seeing here? You are seeing only 1s and 2p orbitals. So only the px and py hybridizes. They separate from this guy. So you have what looks like this. So this is the 2s, 2py, and 2pz. So the s orbital, so you have what looks like 1, 2, 3 like this. So the s orbital is the pz orbital is separate, but you see only 1s and 2p hybridized together. So, and that's how they form unsaturation, the first level of the first degree of unsaturation. Okay, then they are common in alkenes. Okay, they are common in alkenes, and they form two bonds. They form double bonds. They form double bonds, which comprise of sigma bond, and pi bond. Now keep in mind also that the sigma bond is the strongest covalent bond. Is the strongest covalent bond. I hope you are seeing what I'm writing though. Is the strongest covalent bond. Now, another thing is that the bond angle is 120 degrees, okay? And it forms a trigonal planar shape, trigonal or triangular planar. So it means it looks more like a triangle, right? Triangular planar geometry or a flat molecule. It forms a flat molecule. So if I put a molecule on the plane of the board now, you won't see any molecules sticking out. Is there any atom sticking out or any bond sticking out of the board? It will lie flat on the plane of the board. So that's what that is about. And this pi bond is the center of organic, and is the center for chemical reactions for this guy, for alkenes. So we see sp2 hybridization in alkenes. So what do you see? How do we see the structure? For this guy, the structure will look something like this. But for this guy, the structure is going to look something like this that I drew here just now. So this is for double bond. So you can see there's going to be a double bond between this carbon and another carbon here. Who will also notice that there is an angle here, right? So this angle is approximately 120 degrees. Is that okay? This one that we draw like this is not exactly like this. It's going to look something like this. Okay, with the carbon being at the center here, with the bond angle around them being 109 degrees. Why is that the case? Now you have to learn about what is called the Vesper theory. Okay, I will link that in the description too, but I don't want to start discussing it here to digress, to shift our attention. Now the other thing is this, sp hybridized. And what Vesper theory is just about is that it's called the VSEPR. That is valence shell electron pair repulsion theory. And what that theory is saying is that the reason why these guys have this orientation is that the electron pairs, the electrons in each of these atoms, they want to repel themselves as far away as possible. Okay? Now, the next thing you must learn, you should also, now the sp hybridized. Sp hybridization is just where only one s and one p hybridizes. So what you have, the 2p, the remaining 2p, py and pz, they don't hybridize. Only 2s and 2p hybridize. So that's why we call it sp hybridization. 1s plus 1p. Okay? So you have 50% s character, 50% p character. So, and it is the second level of unsaturation. The second level of unsaturation. It forms triple bond. Triple bond is formed. Now, in that triple bond, you will have 2 pi, 1 sigma, and 2 pi bonds. Is that clear? Now, the other thing is that it is formed in alkynes, okay? Formed in alkynes, and I'll tell you what they are, those alkynes and alkanes and those things. I'll tell you what they are. But of course, if you would need better details on them, see the link in the description for all those videos. Now, like I said, triple bonds, 1 sigma, 2 pi's. The bond angle is 180 degrees. And what is 180 degrees? Angle on a straight line. So it forms a linear geometry, linear angle, linear bond angle. So it has a linear geometry. Okay? So that's what you will see. That's why you see a shape that looks like this. 1, 2, 3, C. So you see it's a straight line between here and here is 180 degrees. Okay? So that's that. And that is primarily what you need to know about hybridization. Now I'll clean the board and then we'll move to the next thing. We'll move to the next thing. Perfect. Are you getting it? All right, so now let's move to the next term. We're at number hybridization. So that's number 3. So let's go to number 4. Now the remaining terms here that I'll be discussing, I might discuss them faster because they are simpler. So you must know what organic compounds are. Like I said, we have talked about organic compounds, which are basically compounds of carbon apart from those guys. But in this case, we want to focus on hydrocarbons. Hydrocarbons. Now, hydrocarbons are the simplest organic compounds. They are the simplest organic compounds. Why? Because they comprise of carbons and hydrogens only. They comprise mainly of what? Carbon and hydrogens only. Is that clear? All right. And hydrocarbons are basically 3 families. They comprise of There are three families of those. They have the alkanes, okay, and alkenes and alkynes, okay. But then there's a special type of alkene that because of their own different kind of reaction, they are called arenes, okay. Arenes are basically aromatic hydrocarbons. And we'll deal with this later, okay. We'll talk about this later. But just know that these are all hydrocarbons. Every other ones that are mentioned apart from this will not be hydrocarbon. So you see which of these are hydrocarbons. You see a question like which of these are hydrocarbons. You see you see which of these is not an hydrocarbon. You see all of this, and then you now see alcohol, for example. It's not an hydrocarbon. You see this guy, carboxylic acid, not an hydrocarbon. Exactly. So those guys, esters, aldehyde ketones, they are not hydrocarbons. Only these guys are hydrocarbons. And these are special alkenes. Now, the next thing we have to learn now is, now that we know the hydrocarbon compounds, let us learn of their functional groups. Yeah, they are functional groups now. They are functional groups. Now, there's something I will do. After now, we are going to learn about the structures, the type of structures that we have. Okay, the structural formulas that we have. I'm going to show you all the structures. I'll use this. I'll use this simple hydrocarbon, the alkane, to teach you the structures. But first, let us learn of the functional groups. And when we learn of the functional groups, we'll be able to talk about naming afterwards. So now what are functional groups? Now functional groups are the ones that they are number one, they are the reaction centers. They are the reaction centers in an hydrocarbon, in a molecule, okay? In an organic compound, they are in a molecule or in an organic compound. And they are the ones that dictate the chemical properties. They decide the chemical properties of the compound. They determine the chemical properties of the compound. That's the functional group. And it is the one that is always given priority. It takes the family name, the chief name, the parent's name rather, in a molecule. So that's the functional group. They are the reaction centers, and they are the ones that dictate the chemical properties and nature of that compound. So the behavior of a compound will be determined by what? The functional group. The behavior of a compound, or an organic compound, is determined by its what? Its functional group. Now let's deal with some functional groups that you have to know. Now the names, we'll talk about their names. Then we'll now talk about the functional group, their functional group. Now the next table I'll draw will probably be the table that shows their, okay, maybe I should also already make the table that shows let me write them in order. Or should I go with simplicity? Let's go with, let's go with in order of complexity. Or how should I go? Let's take it this way. See. We'll do that again. So alkynes now. Alkanes. The alkanes, they have the functional group C single bond C. So like this. So C to C bond here is their functional group. That's their functional group. What about alkenes? Now alkenes have a structure that looks like this. Their functional group is C double bond C. This is their functional group. And of course, you might have H's attached. So but this C to C here is their functional group. This is their functional group. So anyone that is attached to this will now be called, I'll tell you about some names too. The name of carbon. We have alpha carbon, beta carbon based on position, okay? Based on position, we'll discuss that. Now, we also have the alkynes. The alkynes will look like this. Of course, that's what I just showed you, the alkynes. But notice, this is their functional group. This C triple bond C, functional group. C triple bond C, C double bond C, functional group. Any carbon attached will now be what? The alpha carbon. Any carbon attached to this one here will be the alpha carbon. There's a carbon here alpha, there's a carbon here alpha. So there will be two alpha carbons here. We'll deal with that in a moment. Now, alkynes. Now, the next one you should now know is alcohols, or no, arenes, alcohols, or alkanols, okay? Generally, we call them alcohols. So alkanols will look like this. ROH. You see, this OH group is their functional group. This itself is their functional group. This one is just alkyl group. So alkyl group might be attached here. Alkyl group are attached here. So alkanols, we have aldehydes. Aldehydes are called alkanals. They are called alkanals. Don't confuse this with ketones, which are otherwise called alkanones. Is that okay? Ketones. Now, aldehydes have their functional group is C double bond OH, and of course, they'll be attached to an R group here. While ketones are R to C double bond O, then R. Okay, let me put at an angle. R like this. So this is their functional group here. They are both called carbonyl compounds. There are actually three carbonyl compounds that you will most likely come across. The carboxylic acids. Carboxylic acids. Okay, they are the organic acids. They have the RC double bond O, then OH here. So this is also carbonyl. They have the carbonyl. What am I calling carbonyl? So they have the carbonyl carbon. So carbonyl carbon simply means a carbon that is attached to oxygen. That's what we call carbonyl. Okay, so those are carboxylic acids. Then you should also know esters. Okay, esters. Esters are RC double bond O, then O to R again. So a different R, for example. So that we R and R prime. So this guy here is their functional group. COO. That's their functional group. All right. The next one you should learn is the amides. Now let's learn of the amines first. The amines is just NH2 attached to an alkyl group. Those are amines. But then there is the amide group. Okay. The amides are basically C double bond O, then NH2. Okay. When we have C double bond O and we have NH. Yeah, so that's amides. Then there is the, so see, primarily for your O level, if you know these ones, these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think these 10 families, they are good to go, at least for a start. They are good to go. Now, when I want to start the name, when I want to name compounds, I'm going to show you other families that you are supposed to know. Okay? So that's it about functional groups. Now, what's the next one? Okay. Now let us deal with homologous series. Then we'll now deal with saturated and unsaturated hydrocarbons. Let me write those down so I'll remember. Homologous series. Then there is saturated and unsaturated hydrocarbons. From here, we'll deal with classifications. We'll deal with classifications. Classification of of organic compounds. Okay, so let's deal with classification. Let me just put it down. Okay, so let's start with the homologous series. Now, what is a homologous series? Please just stick till the end of this video. You are going to understand. I promise you. Now, a homologous series is, what does homo mean? Homo means same, right? Homo means what? Same or similar. Gos, there is talking about, oh no. Homologous, logo there is study, right? So, but basically what homologous series refer to is group families of hydrocarbons or families of organic compounds that have, number one, the same molecular formula. They have the same molecular formula. They have the same general, did I say molecular? Sorry. They have the same general formula. General formula, what that means is there is a general, so we'll talk about types of formula now. Structure and formula. We'll talk about formulas too. So homologous series will be number 6, right? So primarily, we might talk about more than 30 things, but at least I put 30 so that will be the list we'll talk about. So they have the same general formula. So for example, we have alkanes. Alkanes have a general formula CnH2n plus 2. Plus 2. But alcohols, for example, we have a general formula CnH2n plus 1 OH. So do you see? All the alcohol molecules that you see, they will be built upon this formula. Exactly. So that's what we mean by same general formula. They also have the same behavior, chemical behavior, the same chemical characteristics or properties. Okay, they will have similar, maybe not same, but similar. Similar means alike. Okay, same means exactly the same. So for this one, is exactly the same. Their general formula is exactly the same. Now, these ones, they also have homologous series have similar reaction, yes. I mean, that's chemical property, okay. Another thing is that they will have similar mode of preparation, yes. So let's still categorize that as chemical property. Another thing is that each member, every successive member will differ by a CH2. Will differ by CH2. Okay, what that means is this. If successive member means a homologous series member. So for example, I have methane. Methane is CH4. But if I have ethane is C2H6. How did I create this? I created this off of the general formula. The general formula, there are prefixes that you should know in naming. I will discuss this in naming. You should know when we have only one carbon in that molecule, that is called meth. When there are 2 carbons, we call it eth. 2 carbons, 1 carbon. 3 carbons, we call it prop. 4 carbons, we call it boots. 5 carbons, we call it pent. If you already understand this, you can fast forward the video to the aspects, because I will still deal with advanced stuff. That I'm dealing with this basic stuff now should not make you click off the video, okay? 5 pence, 6 hex, okay, 7 hept, 8 oct, 9 non, 10 dec. Of course, there is 11 to 100 above, but I want to stop here, okay? Now, I mean, of course, I think I named some that are greater than this, that are greater than 10 carbon. Then you are okay. So now these are the prefixes, okay? When it is 1 carbon, it means N is 1. I want to create a homologous series now for alkane. Alkane homologous series. I want you to see this. Apply. Now, CnH2n plus 2, this is their general formula. When N is 1, carbon will be 1. So 1 carbon, H2 into bracket 1 plus 2. So 2 times 1, 2 plus 2, that's 4. So that's why you have methane to have the formula CH4. Now what about the second one? F, 2 carbons. So N will be 2. So that will be C2H, 2 into brackets 2 plus 2. This becomes C2H, 2 times 2, 4 plus 2, that's 6. So F, 2 carbons. A, this A represents the family name, alkane. Exactly. This will be C2H6. C2H6. Now the next thing, so the next one, three carbons. That will be C3, H2 into bracket 3 again, plus 2. I just substituted 3 into this equation for N. So we have formula rather for N. So that becomes C3, H2 times 3, 6 plus 2, 8, C3H8. Now what do you notice? Propane, I said, is what? C3H8. Now what do you notice? The difference between each carbon is 1, 1. C1, C2, C3. So it is 1, 1 carbon, but that they differ by. That's C1. How many carbons how many hydrogens? How do the hydrogens differ? 2, 2, 4, 6, 8. So each member that is following each other, that's not successive. They differ by what? CH2. Now that you know this, let's go to, now the other thing is that their physical properties also change gradually, okay? As you go down, the physical properties change gradually. What that means is this. The physical property is quite consistent for some number of homologue. Each member is called a homologue. Each member is called what? A homologue. So for example, methane, the first four members, methane, propane, for alkane now. Methane, ethane, propane, butane. They will be gases. See, that's consistent. But from pentane upwards, pentane to like C9, to C17 rather, this one will be liquid. Then from C17 above, C18, C19, that's octadecane, nonadecane, above, they will be solids at room temperature. But the first four, gases at room temperature, next 10 or thereabouts, solids, liquids at room temperature, and the bigger ones, solids at room temperature. So you see that the chemical property is increasing gradually or changes gradually. So it means that it is consistent for a number of homologue. So that's that about homologous series. Number 7, let us talk about saturated now and unsaturated hydrocarbons. Now these two, saturated and unsaturated hydrocarbons. Now these two names I mentioned here is the broad grouping of hydrocarbons. So the broad grouping. So whichever family you belong to as a hydrocarbon, based on your reaction, you will either be called saturated, based on not just on your reaction though, but this saturation and unsaturation actually has a very big deal with their I think I need to take water. With their chemical reactions. Now, the saturated, like I said, how do you write that there? Okay. The saturated, like I said, are those ones that, when you call a hydrocarbon or an organic compound saturated, the first thing is that all the carbons have single bonds all through. All the carbons have what? Single bonds all through. All the carbons have single bonds all through. Then, while the unsaturated have one or more double or triple bond. Let's just say multiple bond. One or more multiple bond. That is unsaturated hydrocarbon. So saturated hydrocarbons are primarily alkanes, are just alkanes. While unsaturated, they are alkanes, alkynes, arenes. Okay? So these ones, they are unsaturated. Now, what is typical of saturated hydrocarbons? Saturated hydrocarbons are the ones that have complete octets using only one single bond around them. These ones have the form double bond or triple bond. Now, one thing with this one is that saturated hydrocarbons, they undergo only substitution reaction. No, not so only. That their classical reaction is substitution. But this one, their classical reaction for unsaturated hydrocarbon is addition reaction. Now, one thing you must know is that, like I said, that, for example, for alkene, which you have this will be the center for that addition reaction. So the addition reaction happens on this their functional group. Is that clear? So their classical reactions are called altogether called addition reaction. While for saturated they are called substitution reaction. I will explain what this means too separately. So those are saturated and unsaturated hydrocarbons. Now let's talk about classification of hydrocarbons. So in the classification, we're going to have the following. We'll talk about open chain hydrocarbons and closed chain hydrocarbons. Open chain hydrocarbons are also called aliphatic hydrocarbons or aliphatic compounds. Then open chain, so that's open chain. Then for the closed chain, let's talk about, we have aliphatic, then we have cyclic or cyclic, then we have the alicyclic, okay, but then there is the open chain aliphatic or acyclic. There is aromatic, there is cyclic, there is aromatic. Okay? Okay, this is way we'll do it. Let's distribute it into two. So we have the open chain and the closed chain. Are you seeing the board? We have the open chain and the closed chain. I know you already know it, but just listen, okay? So inside the open chain, we have aliphatic guys. We have only the aliphatic. But then in the closed chain, we have the cyclic. The closed chain is also called cyclic. And we have the alicyclic and the aromatic. Okay, but then there is now heterocyclic. So it is from here we should move to structures or formulas. So what are open chain or aliphatic? Open chain simply means the hydrocarbon or the compound consists of straight chain or branched structures, branched molecules, or branched chains. That's what we basically use. Straight chain or branched chain. So what that means is this. Look at this. We have this. You notice that this is a straight chain, right? In fact, sometimes we might draw it like this, and then students will be confused and they'll say, now here is the truth. This bending that we did here is unnecessary. Is that correct? We could have just taken a straight guy here, but sometimes you might see questions that might want to confuse you. The only time this is necessary is if this were to continue like this. Then this bending here is not necessary. Now this thing you are seeing here is branched because there's a branching here. If you want to go straight, this here will go straight. You will pick that longest, think of it like a tube. That longest tube, that will be called the parent chain. So once there is a branching off, then so that's branching, or a kink. It's called a kink, to branch off. Another the reason why I clean this is because I could show you that I want to show you that it also could be written like this. Two C's here, right? So two C's. Then our CH3 will just come here. Do you see? We can go straight and then see our bend. This kink here is going to be this kink here is going to be a substituent. Okay? How am I feeling tired? Then there is alicyclic. Ali from aliphatic, right? Then cyclic. So what that means is this. These guys are cyclic. They are cyclic. What cyclic means is that the first carbon bonds with the last carbon. Connected, first carbon is what? Connected to last carbon. So for example, this is what, if I start numbering from here, carbon 1, carbon 2, carbon 3. Carbon 3 is bonded with carbon 1. So okay, I could have a shape like this too. So this, if I say this is carbon 1, and I'm deciding the presence of substituents might direct my naming, my numbering here. Okay, but here, I just want to go one, I can go from anywhere. 1, 2, 3, 4, 5, 6, 7. And the reason why I'm going from any direction is because there is no substituent. So any direction is okay. So these are 7 carbons, and you see these 7 carbons attached to the first carbon here. You see it? So that's why it's cyclic. That's why it's cyclic. If I were to stop here like this is not cyclic. Don't let it confuse you, even though it looks like it's rotating. It's going around. So it's not closed. So now, why do we call it alicyclic? Alicyclic because it consists of non-aromatic carbons. Okay? Non-aromatic carbons. Now, what are aromatic carbons? Then I'll discuss what this is. You see, alicyclic simply consists of, maybe you might have straight chains to attach to it. Okay, this thing I drew is called skeleton structure. That's what we'll deal with next. But you just listen and try to get this. You see these guys, the carbons here, there's nothing that is, it could be saturated too, okay? It could be saturated, unsaturated. But one thing you will notice is that it's not aromatic. So since it is not aromatic, it will consist of branched or straight chain hydrocarbons and or cyclic but non-aromatic what? Hydrocarbon. So we have aromatic and non-aromatic hydrocarbon. Non-aromatic can also be called what? Alicyclic. Non-aromatic are the ones that are still cyclic but are not aromatic. Now, more on aromaticity, check the video in the description. But of course, one thing that you must know about aromatic is that any guy that is born on benzene ring, that has the benzene ring, is aromatic. Okay? So this is the benzene ring. I'm going to draw just one canonical structure. So, but the general resonance hybrid is drawn like this. So this is the best structure that represents it, the cycle. So this is what I'm supposed to draw. But I just wanted to show you this so that you will notice something. Aromatic because of several characteristics. The characteristic that it is cyclic, you can already see this is a cyclo group. Another thing you will see is that I said it's cyclic. Another thing you see is that it is conjugated. Now, what does conjugation mean here? Conjugated means that you have alternating single, double bond. Is that okay? So it's a conjugated ring. Then another thing is that it follows Ockel's rule. Now, I'm not going to tell you what Ockel's rule here. See the video in the description, it will help you to know it. It has 4n plus 2 equal to number of pi electrons. Okay, so that's that for aromatic hydrocarbons. Now, another thing you should notice with cyclic alicyclic guys is that they usually have two less hydrogens than their corresponding aliphatics. So an alicyclic hydrocarbon will have, by the way, this one is also called acyclic. Acyclic means not cyclic. They will have two hydrogens less than their They are non-cyclic or acyclic corresponding acyclic hydrocarbon. Let me show you what that means. Look at this guy now. This is cyclic, right? To draw this thing in full structure, this is the way it looks. Carbon is bonded to another carbon. Single bonds, that's why you're seeing that there. See, this, I want to relate this and this guy. Sorry. This, how many carbons are here? This one, each vertex represents a carbon. 1, 2, 3, 4. So we have 1, 2, 3, 4 bonded. This carbon already has 2 bonds around it. It needs 4 more, right? 1, 2. This guy, 1, 2 also. So there has to be 4 bonds around it. This guy, 1, 2. This guy also, 1, 2. Now what do I want you to see? Here's what I want you to see. How many carbons are here? C, 1, 2, 3, 4. 4 carbons. How many hydrogens are there? 1, 2, 3, 4, 5, 6, 7, 8. H, 8. But actually, and this is cyclobutane. This is cyclobutane. Now, one thing you notice is this. With this cyclobutane, normal butane, how does normal butane look like? Normal butane looks like this. N-butane means normal butane. Looks like this. 1, 2, 3, 4 carbons. So how many hydrogens should be attached? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Notice that I am counting the bonds so that it will be 4, 4 around each carbon. So how many hydrogens are we going to attach? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see that that guy is having 10 hydrogen. This guy here. This guy here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. And this one here has 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. So this one is C4H8. This one is C4H10. But notice it's butane, right? But this one is cyclo. So the cyclo group always has 2 less hydrogens than their corresponding aliphatic hydrocarbon. Is that clear? That is what I was pointing out. Alright, so that is that. The next one is formulas. Let's talk about formulas. Now with these formulas, I will only emphasize with alkanes. We have different formulas. We have, the first one is the molecular formula. Molecular formula is gotten from molecular formula. Then we have structural formula. And we have the skeleton structure, and we have the condensed. Now in this structural formula, I mean the displayed formula. This is to display something. That's what I mean there. So using alkanes, let's just deal with 4 successive carbons. No, yeah, 4. So we have, let's start with methane. Methane, the molecular formula I've calculated it before, right? It will have the formula CH4, right? For ethane, it will have the formula C2H6, right? For propane, it will have the formula C3H8. For butane, we just saw, it will have the formula C4H10. Now this that you are seeing here is the displayed formula. So the displayed formula for methane will look like this. 1 and 1 carbon, then 1, 2, 3, 4 bonds around it. So you have your H's. If I just draw the bonds without putting the H, it's not methane. Ethane with 2 carbons, so we draw like this. 1 carbon to second carbon. Then you have 1, 2, 3, 4, 5, 6. So 6 hydrogens. 1, 2, 3, 4, 5, 6. Ethane. Propane as well. Displayed structure will look like this. So if I leave it like this is not propane. This is just the skeleton. So we'll now draw this. What I call the skeleton, you can also call it the backbone. So if you don't put the hydrogen, it's only backbone you have drawn. You have not drawn the molecule. So you must add the hydrogen. Well, how about the skeleton? What's the skeleton for methane? There's no skeleton for methane. No skeleton. No skeleton structure. But what will be the skeleton structure for this? Just a line. Why? Because this end represents a carbon, this other end represents another carbon. Is that clear? For this guy also, there are 3 carbons, so to look like this, you should create a kink, a bend. So when you create a bend like that, this will be a carbon, and a carbon. So that's propane. For butane, that will be C4. That will look like this. 1, 2, 3, 4. 1, 2, 3, 4. This is butane. Is that clear? How about pentane? 5 carbons. Now you start counting like this. 1, 2. Is that okay? So 1 as you put your pen on the paper. 2, 3, 4, 5. So this will be pentane. How about nonene? That's 9 carbons. Nonene. Nonene will look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that clear? But how about the condensed formula? The condensed formula of this guy is equal to the molecular formula, which is CH4. What does condensed formula do? It will take the structure as it is, okay, and write the way it is appearing in the split form, but it will try to make it smaller. So look at this guy now. To make this first in the condensed structure to look like this, C, the first C is bonded to 3 carbons, so we have CH3. The next C is bonded to another 3 carbons, CH3. This is the condensed formula. Is that clear? Then how about this one? The condensed formula will look like this: CH3, CH2, CH3. Is that okay? Now the next case will be what? CH3. There will be a CH2 here too, and another CH2, and then the last one CH3 to identify 4 carbons. But there is another way we can write this. The other way we write this is like this: CH3. CH2 appears how many times? There 1, 2, 2 times. 2. Put 2 here, put it in bracket, then 2, CH3. Now, why can we not write this for CH3 and CH3 and put 2? Is because these ones are terminal. Their terminal means they are at the end. Is that okay? So, now, so that's that 4 condensed formula. So it means if it was CH10, C10H22, I want to write it to be CH3, then CH2 will appear 8 times, close bracket, then put 8, then CH3. That will be C10H22. So that said, now we know the structures. Let us clean and we'll go to the next thing. Let me clean the board so that I'll think of the next thing.